the antennas, and this was a picture with which we ended last time. And I also told you about the antenna we had in Russian and in Gombin, but then I realized that I make a mistake by not telling you the even more interesting story, namely when the radios were first used, there were no actually lamp amplifiers and lamp radiators. Everything was done essentially mechanically. The waves were generated by some kind of mechanical devices. And one of those devices, which is it's a patent for it, was done by the Swedish engineer Alexandersson, and that is a not lamp, but it's in this sense mechanical device which generates very long wavelength radio waves. Why do the people were very busy with having a very long wavelengths? Because the communication with the ships on the ocean, you have to communicate it very far, and they didn't know that they can use the short waves scattering them from the ionosphere, so they had to have a long wavelength waves to propagate over enormous distances, and the other was to communicate with the submarines. So right after the First War, there was a big business in building those things, and the lamps were in its infancy, and basically they were in operation in the 1920s. But before that, the only real beauty mechanical device generating those very long wavelengths was this generator by Mr. Alexandersson. And there's only one still in operation in the world. Is somewhere in the middle of nowhere in Sweden. There was a radio station to cover the whole Sweden, and it has this thing, and it is switched on. It's kept in operation, and it's switched on, I'm told, twice a year on some sort of a holidays. And I had forgotten on what kind of holidays. I bet it's for the midsummer, which is a big holiday in Sweden. So that's probably is one day, but maybe, I don't know. Anyway, they kept it operation, and they switched it on twice a year, and it's operation for 15 minutes. But why it is interesting? Because we are in Warsaw, and this is a picture of the Alexandersson radio station in Warsaw. In the 20s, the radio business in Poland starts by a private company. There was a private company which was set by the group of engineers in Warsaw, which got a sort of state-guaranteed monopoly for a while. And that in the 30s, it was in more or less strange way converted into the state-owned radio. But before it, it was a private company which used even the name a Polish radio station. And in addition to this main radio station, which was in a historic building which still is used by the Polish radio, it's next to the Łazienki Park. So if you walk over in the front of the stadium, of the soccer stadium, then there is a sort of a one-floor building, and that is the historical seat of a Polish radio, which still has a program, one of the channels of the Polish radio. And the main radio is on Malczewskiego Street, not far from away, which is a prison that was built by security forces in the 50s as a prison. And before they managed to have it operation as a prison, it was Stalinist times is over, so that was turned into a radio, and if you go inside, you can see that it was a prison because it has a strange built staircases, and there are these nets between the between the different floors, so people couldn't jump from one floor to anyway. So in the 20s, the Aleksanderson radio station with Aleksanderson device was built in Warsaw, in Bornerowo. This is along the highway which goes to Poznań, which is on the west of Warsaw. And this is the original picture of it. This was a very, very long wavelength antenna, which was used to officially to communicate with the Polish population in the United States. And during the war, it was extended during the war, Second War. It was used by the Germans to communicate with their submarines. And it was, at the end of the war, blown. So it does not exist anymore. But I'm told that if you walk over, there are nice woods there. So if you walk in these woods, you can still find the foundations of that antenna, and also there are shacks, what was left from the building of that radio station. So that is a historical information, which I think it's also nice to know some history, not only equations. So let's discuss how the antennas work, and the first and the simplest model which can be solved in a finite amount of time is a radiation of a dipole. As you remember, dipole are these just two charges which are separated by the certain distance, and if you make it so that these two charges are moving periodically, then it is basically the same thing as having an electric current flowing into a short distance, and the intensity of that current changes oscillatory in time. So this is a picture here. We will this thick line is the dipole. It has a length d, and I use the coordinates where the dipole is located along the z-axis. But we will do the calculation in a spherical coordinates, and you had to believe me that I did the correct transformation of the vectors into the spherical coordinates. So we have this little wire, and there is a current which is periodically in time changing in that current. So the current density J is an intensity I sub 0. Now, since it is a very thin wire, then it's localized so I can write it as a delta function in the x and y coordinates, but it's extended along the z coordinate. Therefore, I use this this versor of the axis z, and then that construction is called the Hertz dipole, and using the formula we had with the green function and everything, we can plug that j into the expression. You remember there was this integral relating a current to the vector potential, so you can do this calculation very easily because of this structure of the current, and the vector potential A sub r is a point far away from the or maybe not so far away, but away from the dipole, and that is the solution for our vector potential. So once we have that solution, and this is the transformation I mentioned, that now I had to write it now in the spherical coordinates. The relation between in a spherical coordinates, I have three vectors. The one is the versor, one is the radial vector, the other is the azimuthal, and the other is the polar angle. So these versors are denoted by ER, which is a versor in the radial direction, E phi in a one angle, and E theta will be into this other one. So the Z components has this form in the spherical coordinates, and that allow me to rewrite the vector potential. And the vector potential has two components, a phi and theta components, and they are written here. And I realize that I missed the current from this expression. So you have to read that D is equal to I0 times D. Okay, and then having the vector potential, that's why we had written those lengthy integral formulas for the vector potentials. I can calculate the magnetic flux, and magnetic flux is rotation over A, and I can calculate that rotation, and it turns out that in a spherical coordinates, the vector potential, the magnetic flux has only the phi component, and the value of the phi components can be easily calculated. And already you should realize that something interesting will happen, because there are two terms in this expression which have a different radial dependence. One is 1 over r, and the other is 1 over r to the power square. So we have two different r dependencies, and that is the important thing here, because as we shall see in a moment, that they contribute to some interesting physical consequences. So let me write it again, and I also can calculate the electric field. And if I calculate the electric field, then I notice again those curious two different dependencies, particularly, okay, now we have this formula should be read with some caution. The product of I0 times D is a dipole moment, because which is denoted, which I believe we denoted as a P, and then I have these different R-dependent terms. And I have let's first think about the term which is proportional to the R cube. And that dependence of 1 over R cube is called near field. Why it is called near field? This is a spherically radiating wave, okay? And we look at the one contribution which has the radial dependences as a r to the minus third power. So let's look now on the sphere surrounding our radiation source. The area of the sphere is proportional to the square of a radius. Therefore, if I calculate the flux of that field over that huge sphere, the flux of that part of electric and magnetic field which depends on R cube over that sphere, then when the radius of the sphere grows, it disappears. So far away, that term does not contribute. If there is an observer seeing, if I had the antenna here, and this is the antenna in this thing, and if I am sitting on the Aldebaran star, I'm not seeing the near field of that antenna, because it goes 1 over r, average over that sphere. So that is the reason why this r cube terms is called the near field. But there is this term which is proportional to 1 over r, and this is called the far field, for exactly the same reason, because it is not disappearing at the long distance. And that is a term which governs radio transmission, because we are not so interested in using radio unless, of course, those people who are sitting in the across the aisle in the subway and communicating with each other, sending SMS or texting to each other, right? But usually we communicate by acoustic waves at the short distances. But if we want to communicate with somebody far away, we nowadays use the radio waves more often than even the coaxial cable under the sea ocean. Particularly, we communicate with radios with the satellites, so the communication now goes mostly via the satellites. So this is what is called the real, there is a reason why it's called the far field. And of course, in the radial coordinates is also this term which is proportional to the r square, which is neither a near field nor the far field. So sure enough, it's called induction zone field. And it is important for engineers building various devices, but we will be not bothering with it anymore. So let's continue with our formula. Let's now calculate the Poynting vector. As you remember, the Poynting vector is a vector with which the energy of electromagnetic radiation flows. So this is a vector product of electric and magnetic field. And since we are working in the complex variables, then in order to calculate the vector, we had to, we discussed it, we had to get the real variable out of this complex variable, and that is why the magnetic field is here with the little star, which is a complex conjugation. And then I'm also going to calculate a mean value of the field over the sphere. So this is this I have to calculate the real part of that vector product. And if I do this, then this equation tells us how this mean value of a vector potential of a Poynting vector looks like. Interesting thing which you have to pay attention to it is that there is this curious square root of mu0 divided by epsilon 0. If you put down some numbers, it has a dimension, and that dimension will turn out to be important in a moment. If I have the vector Poynting vector, then I can integrate that vector over a surface of a sphere, and then I will get the energy which is radiated by my dipole, and that's a very simple calculation, and that is a formula which you have here. And as you see, this is mean energy is proportional to the square of a ratio between the dipole length and the wavelength of the emitted radiation. That, of course, means that if the d is very small, then this radiation is also very, very small, particularly when the wavelength is large. So, so anyway, that is a formula, and again there is the square root, which is of some importance. And sorry, because I lose my glasses. And I can parameterize this energy emitted by my dipole by a formula which is borrowed from our talks on electrostatics. Namely, I can parameterize it by dividing by that if I divide the energy by the square of the current, then I will get the resistance. So I can do this, and since the mean value of a square of a sine is equal to 1/2, then all of a sudden I can calculate it, and my result is that this is the amplitude of the I times the square times r divided by 2. So if I have that, I can calculate this resistivity, and if I plug into the formula, I will get again this interesting formula. And d over lambda is dimensionless, so that square root have a dimension of the resistivity. So this is what is called radiation resistance. And as you see, it has a certain coefficient, which gives it the value, and we will soon calculate the number. And then it's proportional to the ratio of d over lambda square. So if the wavelength is large, then this is a small number. If I want to use the antenna, I have to feed it with the electric current, so I have to connect it into the circuit. And that circuit will also have the impedance. So the total impedance, the contribution from the dipole is very small if d is infinitesimal. So if I have this very small antenna connected to the circuit, then most of my energy will be dissipated in the circuit, not in the antenna. So from that reason, our calculations are not really very realistic, because we don't want to waste all the electric energy into the system without sending effectively any energy out. So we have to do something now. And the only thing which I can change in this calculation is to do the calculation when this dipole is not infinitesimal, right? I had to get rid of the assumption that this is that these are just this little kind of d. So how I can do this? I have do the calculations assuming I have a finite wire over which the electric current flows. And then the calculation becomes a little bit complicated. There are lots of trigonometric functions which are going back and forth, so I believe we will not discuss that in more detail. But this is a picture which in a graphic way tries to tell how the radiation is generated by the two moving charges, by this little dipole, but that we will not talk about it. So when the dipole is finite size, then the solution for the energy emitted by this antenna is having a still expression which I can write on one slide. And this is the integral. And this integral can be expressed in terms of special functions, because I believe you are not that well. I mean, we will have to lose a lot of time of discussing the properties of some special functions, so let's forget it, and let's do these calculations for a very special case, where the wavelength and the ratio are equal, and the length of the antenna are equal to pi. Okay, that means that the antenna is total length of antenna is equal to the is related to the length. So basically, they are very of the same size. Just the factor phi is there. So if I make this assumption that k, which is 2 pi over lambda, right? So the k is 2 pi over lambda. So if I have a 2 pi over lambda times d, then the pi cancels, and d over lambda is equal to 1/2. So that is shown on the picture. Okay, if this is called the half wavelength antenna. And then the energy emitted is having a very simple form. And I can then calculate the radiation, the resistivity of radiation, and it turned out to be just a constant. And now I can calculate the square root of mu0 over epsilon 0 using the values of mu0 epsilon which we had on one of our first lectures we have. And that is a Kabbalistic number 73 ohms. And that is the reason why the transmission lines, I mean, with the resistivity 75 ohms are so fashionable, because they are very good fit to the resistivity of that antenna. What is the problem with my antenna? The problem with my antenna is that it is an antenna which is emitting everywhere in a full sphere. We are working in a spherical coordinate. For applications, not that very often the spherical and the emission for wavelengths which go over the whole sphere are very useful. And the engineers are building directional antennas. We need to send the wave to a satellite. I mean, look at the antennas. We need to pick up or send the wavelength to the satellite, which is at a given point in the sky, if it is a geostationary satellite, right? So I don't need to send it everywhere. I just need to send it in direction. And of course, if the antenna is not a spherical, a symmetric, then the calculations are become really very, very, very complicated. And the last part of my lecture today will be about what is called the Lorentz Reciprocity. This is an identity from it's a certain property of a Maxwell equation, which is extremely important to understand what happens if I have an antenna which emits the radiation, and I have another antenna with which I pick up the waves. Because I'm not building a radio just to emit the waves. There's somebody who wants to listen to what I'm emitting. Therefore, I have to understand what is the relation between the radiator and receiver. And this is a picture I had in mind. I have an emission circuit where I have a certain voltage which is fed to the antenna, and there is a recipient circuit which picks it up. And let's start looking at it, analyzing the following property of a Maxwell equation. Imagine I have two sets of electric and magnetic fields, E1 and E2, H1 and H2, and each of them is a time dependent with the same periodic frequency. It's a periodically in time dependent changing field with the frequency omega. So when I have it, then unfortunately I'm going to force you to look at this very lengthy expression. Let me calculate first the scalar product, which looks like a Poynting vector, but it's the vector product of electric field 1 with the magnetic field 2. Okay? So I have electric field 1 takes a vector product with the magnetic field 2, and I subtract it from the vector product of electric field E2 with the magnetic field H1. And I can calculate that vector, and then I calculate the divergence of the difference. So then I have a divergence of a vector product, and I can work it out in the coordinates, and that expression can be written in the form that this is magnetic field, scalar product with the rotation electric field, and then there is an electric field times a rotation of a magnetic field. The reason why I have done it is that the rotation of electric field and the rotation of magnetic field, that these are expressions with features in the Maxwell equations. So I can now use the Maxwell equations to replace those rotations with the time derivatives of the magnetic flux and the displacement vector. So if I do this, my expression becomes a little bit less complicated. It's still a lengthy formula, but because of the electric field and the magnetic field are oscillating with the same frequency omega, then in each of these formulas, I can replace the time derivative by the multiplication by the I times omega. So differentiation disappears, and my formula, when I replace each of those time derivatives, will become much more simple. And if you work it out, everything cancels, and it turns out that this divergence is equal to the electric field 2 times the electric current 1 minus electric field 1 times the vector current 2. And then I do the integration. I integrated both sides of this equation, and I find out that the volume integral of this simple scalar product is equal to the integral over a volume of a divergence of something. But if I have a divergence of something integrated over volume, then I can replace it by the integration over a surface, by Stokes or Ostrogradsky Stokes, whatever is the proper name of that formula. So when I do this, then I have the integral, that the integral of a volume is equal to the integral over a surface. And that's a very, very beautiful expression, because you immediately realize why I was talking so much about the near and far fields. Because I have a volume, I have my antenna and receiver, they are in a huge volume. Now I have the integration over a surface of that huge volume. So the contribution to the integral, which is on the right-hand side, will be different for the near field and for the far field. And sure enough, when I substitute it, then it's very easy to observe that the contribution of a near field is completely negligible. So I have this integral over the surface, where I can ignore the near field term, which I had, and only do the integration with the far field. And that integration with the far field is relatively simple, and the formula is that the H1 turns out to be given as a vector product of a wave vector times E1, and E2 is given by the same formula. So now it is trivial. It turns out that this product is 0. So since the product is 0, all of a sudden I derive the identity. If I just have two sets of electric and magnetic field, whatever the space dependence, it's important that they oscillate with the same frequency. But two arbitrary sets, for two arbitrary sets of electric and magnetic fields oscillating with the same frequency, that kind of integral is identically equal to 0. And that, of course, is a property of a Maxwell equation. So it has to be valid whatever we do. Whatever ingenuity of engineers to generate these electric and magnetic fields is, and the producing the currents is, then this thing is holds. And that is called the Lorentz Reciprocity formula. And that is, of course, what Mr. Lorentz has derived, probably before the Marconi built up the first radio. Okay, so there are some conclusions. And the simple way of getting those conclusions, which are generally also valid, are when the two antennas are emitter and receiver are infinitesimal. If they're infinitesimal, then I can do these calculations, and the calculation is pretty good. The integration over the volume can be now done over the volume of the antenna, and the volume of the antenna is the integral over of the length and the surface, and the surface is the same for both of these antennas. So the integration over volume is now the integration over length of the antenna and the surface. The current, if the antenna is infinitesimal, is constant. So actually I only have the integration of electric field along the wire of my antenna, and the integration of electric field along that wire is just the voltage. So that for infinitesimal antennas, the formula, the Lorentz reciprocity, becomes extremely simple. It tells me that the voltage of the first antenna at the point of a second antenna times the second current is equal to the voltage of the second antenna on the first position divided times the current at the first antenna. So I can divide it, and the ratio of these voltages to the currents is the same. And that is one of the basic reciprocities used by the engineer for building the antennas. Let's think for a second about more properties of that sort. And the one is the property which engineers called antenna gain. What is the antenna gain? Let me first write the formula and then tell you what it is. We have the antenna, and it emits radiation. So I go over and I choose a sphere which has some units radius equal to 1. And I calculate the mean value, the absolute value of the first absolute value of a pointing vector on the surface with radius 1. And that divided by the energy on that surface. Okay? So because I fix the radius, then it's a function of two angles, theta and phi. So I look up for the maximum value of this function in two variables. That is a variation calculation in mathematics. Mathematicians tell us how to do this calculation. And that is what we call the gain, antenna gain. Is a ratio, I compare the flux of the energy over the surface of this unit sphere over the energy. And then if I have two antennas, I can define what is called the antenna area. That's the complicated notion. What do you mean by antenna area? This is something which is, roughly speaking, for a physicist, the good definition of that surface area for a physicist is a cross-section. I mean, you have been taught in the courses that in the quantum mechanics, that if I have a target and I shine the radiation or I throw the particles on it, then depending on the interaction of this radiation of the particles of light which comes to my source is measured by something which is called the cross-section. So that is, for example, if you have the sphere and you shine the light on it, classical light, then the shadow behind it is a good definition of that cross-section. Well, the there are problems, because if that radiation coming will be a matter waves, the Schrödinger waves, then this cross-section of a sphere turns out to be not a shadow, but the whole surface. But that's a subtlety of a quantum mechanics. But basically, antenna also has that cross-section, which is called area, and then there is a formula which follows from the definition of a gain, that the ratio of the area of antenna to the gain of the antenna is constant. No matter what you do, if you have two antennas, that is the formula which is there. And all of them comes out from this Lorentz reciprocity. So as you see, basically, if you want to be employed into radio company or anything which sends electromagnetic waves, what you really have to do by heart is the Maxwell equations. This is a picture to show various kinds of antenna which we have, and they are built up for various purposes, and there is a whole chapter of applied mathematics which goes into the calculation of the properties of the antenna. And everything was fine, because antennas could be big and there was no problem, they were sitting somewhere. If not that the people wanted to have devices which are slightly smaller. I don't know whether you have seen the movie, which is called The Gold for Brave. It's one of the Second World War movies when the bunch of American soldiers are stealing a German gold stored at the end of the war, stored in some remote place, and the hero of that film is Clint Eastwood, is a person, the actor who plays that person is a Clint Eastwood, and he is carrying a cell phone, a portable phone from the time of the Second War. And you should see it, how it looks in the movie. It's like a portable phone we have nowadays, but that size. And it has a very lengthy antenna. So the antenna is almost as long as a gun of his tank. So that was very not comfortable to have those antennas, particularly when the people go into the very short wavelengths, and they start building something like real cell phones. The first cell phone, which Marty Cooper used for his first talk, it was that size. And the only problem was that it was good for just one talk lasting 5 minutes, because it had a very small battery at that time. The first cell phones which were in this country in the 90s, they were called heaters, because they were consisting of a cell phone plus a plastic box with the handle to carry, which had the antenna and the battery in it. So all those businessmen at that time, they were known for walking around with those cell phones and those the heater is a an English word for it, but the word we use for those heaters, like there in the corner, is calorifer in Polish. So they were used calorifers, and there were lots of jokes about it. So the problem was that the engineers had to invent much better antennas, and they had to make these antennas as small as possible to fit into the devices we use, and also to be operational. And that is what I would like to show you. This is a copy which I copy from the advertisement of the company making a cell phone, HTC. It's the Taiwanese company. And what you see on that picture is where in this phone there are antennas. Every non-metal part of the phone is used for antenna. So whatever is, if you will dismantle your phone, don't do this, then you will find out that essentially everywhere there are these antennas, because this phone had to have the antennas for I mean, initially there was just one frequency on which they were operating. Now the cell phone had to have a frequency for Europe, for United States, and for Asia. So it has 3 antennas at least for the radio communication, for the phone communication. Then it has the additional antenna which picks up the Wi-Fi, the internet. Then it has another antenna for a Bluetooth communication. So there are almost 5 antennas, not mentioning those antennas built in your cell phones by a company which want to spy on you. They will not tell you where they are, but I can assure you that the phone which I own, which is actually a very good one, I make advertisement for the company, but that's a phone of the Chinese company Huawei. Then there's a city legend that inside of that phone, it's another antenna which connects it directly with the special division of a special organization of a Chinese army. Huawei is actually a company owned by Chinese army, and they don't need to break into the Facebook. As Cambridge Analytica, they already are aware of whatever we are talking here. So don't be. And okay, so that is a story of the antennas. And from next lecture, which will be not next Friday, but in 2 weeks, we will be talking about the optics. And the optics is something which, you know, from the high school, it's geometric optics. And basically it looks like, I mean, as when I was in the school, then the optics was something which you did with the rulers. There were lenses, and you had put the lens and draw the lines, and that was the easiest way of solving the problems. But the optics, the light, is also electromagnetic wave. So all those properties of the lenses and whatever is we will be having a time to talk about is also something which can be derived from the Maxwell equations. So we will start with trying to derive the scattering laws and having a proper definition of what is the diffraction and so forth from the next day. We have the long holiday, so I hope you will be able to enjoy it. The stores will be shut down, so get yourself something to eat if you stay in town, and if you travel somewhere, have a good trip. I mean, I was told that the Polish airlines will go on strike next week, so if you want to fly, then it's probably better to use the other airline, the Polish airline. That's cute to have a go on strike on the May 1st, and May 1st is of course a holiday which was. You know why that we have the 3rd of May is our Constitution Day, and the 1st of May is what we still kept as a holiday from the only reason why it couldn't be dismantled by the present government as the communist holiday is that this was a holiday which was illegal holiday, so to say, during the previous times, and even under the when Poland was divided, this was a day where it was a major demonstration. So that will be one fresh day. Then then on Wednesday somebody will be still working, but enjoy the weekend. It's long, 10 days of vacations.